Hi everyone, this time we are going to study normal and convex fuzzy set. Apart from defining these two types of set, we'll discuss few of the examples of both normal and convex fuzzy sets. So this time we start with normal fuzzy set. So if the membership grade of any fuzzy set, say mu x is equal to 1, for say any x, or if we can say if there exists small x in x such that mu x is equal to 1, then this set is said to be a normal fuzzy set. So let us recall one more thing. Here capital X is our universal set. So this is just to recall, and mu a represents the membership value. Okay. So for example, if we consider a set, say X has three elements 1, 2 and 3, and if we represent the fuzzy set as, say, A is equal to, at 1 it takes value 0.1, at 2 it takes value 0.8, at 3 it takes value 1, then this set is a normal fuzzy set because at one point it is taking value 1. So this one is a normal fuzzy set. If we move to subnormal fuzzy set, this just means that, what do I mean by subnormal? It means that a fuzzy set which is not normal. That is mu a x, the membership grade is less than 1, and this holds for every x. That is, at no point membership grade is equal to x. For example, if we write a fuzzy set, say A, as this, we are considering the universal set as the same, and if we are writing the fuzzy set as say 0.1, at 2 it is 0.9, at 3 it is 0.8. So now this set is a subnormal fuzzy set. Why it is subnormal? Because at no point it is taking one value. At 1 it's taking 0.1, 0.9 and 0.8. So this fuzzy set is a subnormal fuzzy set. So let us move and understand the membership grade through representation. Now we have two examples here. One is say A, another set is say this one is B, and let this one is A. So which, can you tell me which one is normal and which one is subnormal? So if we see the first one, so there's a point, here is the point where it takes value 1. So first one is a normal fuzzy set. Let us move to second one. If we see, the largest value it takes is this one, and which is less than 1. So it means that mu bx is less than equal to 1, and this is true for every x. So that is why this one is a subnormal fuzzy set. And for ax again, we can write here, so there exists x, which is in capital X, such that this is the point where mu ax takes value 1. So that is why it is a normal fuzzy set. Let us move to one more example. So this is our example. So we have to check whether this is a normal fuzzy set or a subnormal fuzzy set. So just by watching this membership grade, we can see that, say at 2, what is the value of mu at 2? So value of mu a at 2 is, you can see it is coming out to be 1. So it means that it is a normal fuzzy set. So this is using one point. I said this using one point. But let us draw this graph, and this is our, let us plot the point. It is starting from 0 till 4. Let us do it quickly. 1, 2, 3 and 4. I hope I made it equidistant, right? So From 0 to 1, it takes value 0. Okay, perfect. Then from 1 to 2, it takes value x minus 1. So we have this till 2. So from 1 to 2, so this is, let me, okay. So from 1 to 2, it takes value this. And then from 2 to 3, you can see it takes value 1. So from 2 to 3, let us make this 3 dotted. It is taking value 1. And then from 3 to 4, it's taking value 4 minus x. Let us plot this. So we have this 4 minus x. Now, seeing this graph, and this is our membership grade, the y-axis, and points on the x-axis. Yes. So you can see between 2 and 3, it's taking value 1. That is, membership grade is equal to 1. So that is why this fuzzy set is a normal fuzzy set. So let's move to another example. In this example, what we do is we are just writing the same example but multiplying it by a number, say 0, and if it is less than 1, and then say 0.2x minus 1, between 2 and 1, and say 0.2 between 2 and 3, okay, and let us say 0.24 minus x between 3 and 4, okay, and the last one, it takes value 0 for all x greater than equal to 4. So if I plot this one, so let us represent this trapezoidal fuzzy set. We have this is x, this is y, this represents membership grade. We can write this as mu, some other say b, because it has different membership grades. So again, it is like say 0, 1, 2, 3, and 4. And suppose this is this 0.2 lies here, okay, and then we have 2 to 3, and then we have from 3 to 4, okay. So its maximum height reaches where 0.2. We can say that, we can see here also that mu b x membership grade takes value always less than 1 for every x belongs to x, okay. So here we have to remove this equal to. So this was by mistake. There is no equal to, it is less than 1. So this is the perfect definition. So this one, all the membership grades less than 1. So that is why this is a subnormal fuzzy set. I hope you got this concept of subnormal fuzzy set. Now we are moving to convex fuzzy set. Now we are understanding this concept of convex fuzzy set, but before jumping to fuzzy one, let us understand what is the meaning of convex set in classical sense, and there will derive the relationship and from where we gradually descended from classical to convex fuzzy set. So in classical sense, students, if you remember, what is the formal definition of a convex set? So a crisp set A defined on the universal set X is said to be convex if X is in A and Y is also in A, its linear combination lambda x plus 1 minus lambda y belongs to A. and where lambda belongs to the closed interval 0, 1. So this is the formal definition of convex set in classical sense. Classical sense, this was the convex set. So if we take, say, any domain, say D domain, if we take 2 points, say X and this is 1 point Y, and we are taking linear combination, that is a line from X to Y. So if this line, students, if this line remains in the domain, if this X to Y line remains in the domain, then we say that the domain, this region, is convex. But if there's a hole in this region or there's a gap in this region, then directly by seeing the region, we can say that the region is not convex. For example, if we take two concentric circles, suppose we are taking two concentric circles, these are two concentric circles. So if we take X here and Y here, and obviously there is a gap, there is a hole in this, I'm filling this gap with red. So if there's a hole in it and we are finding a linear combination, if we take a linear combination of this, so this line does not lie in R. If R is a concentric circle, R is this region, R is this region. Does this line lies in this region? No, this line lies outside this region also. And where is outside? This is the gap region where this line lies. So that is why this set is a convex set. However, this is a non-convex set. Similarly, students, we can define convex in fuzzy also. So moving on to convex fuzzy set. Remember this formula? Remember this formula definition, classical sense? We are uplifting, we are upgrading from classical to fuzzy. Okay. So in fuzzy, a fuzzy set A on X is said to be convex if and only if membership grade of this linear combination, which we wrote in classical students. So lambda x plus 1 minus lambda y is greater than equal to minima of these two membership grades. That is, of membership grade of X and membership grade of Y. And this should be true for all X and Y in the universal set and for all lambdas in the closed interval 0. So this is a formal definition of a convex set. Now students, so the gap thing or the whole thing which I told you here, which you understood here, I hope you understood it. This can be similarly said in fuzzy in this sense. Suppose I'm talking about the triangular fuzzy set. So this is our triangular fuzzy set, X, Y, and here we represent the membership grade. If the fuzzy set, triangular fuzzy set is like this, so you can take the triangular also, or maybe this one also. So again, I'm taking as triangular. So yes, so this fuzzy set is a convex fuzzy set. Why? Because there is a no break in this. There is a no gap in this. There is no hole in this. So this is a convex fuzzy set. However, if you want to see this, why I am saying this, this is by just watching this this diagram. How this is a convex fuzzy set. We can see here, we can take a point, say X here, and let us take another point, say Y here. So this is our mu A X, and this is our, say, mu A Y. Okay, so this is Y and this is X. So if we take a linear combination, if we take, say, lambda x plus 1 minus lambda y, it lies somewhere between X and Y. So we can take it, say, here, somewhere Let us call this as T. This linear combination as T. So it lies somewhere here. And if we take here, so this will be mu T, mu A T. So we can always see that membership grade of T is always greater than minima of these two membership grades. This is membership grade of X, this is membership grade of Y, and the green line represents membership grade of T. So this one is always greater than minimum of membership grade of these two. So we saw that this is a convex fuzzy set. Let us understand what do I mean by having a gap in the region R in convex set. Suppose we have another fuzzy set like this. Yx, this represents the membership grade. Okay, suppose we have this. We have this, then this, then this, and this. Okay. Now let us take 2 points. Let one point be somewhere here, x. Let another point be, say, here, y. Let us take a linear combination lambda x plus 1 minus lambda y such that it lies here. Let this be, say, some t. So it lies here. Now see the membership grades. Membership grade at x is here. So this is membership grade at x. Membership grade at y is, say, somewhere here. So this is for y. And let us see the membership grade for t. So this is membership grade for t. So this is mu a t. So we can easily see that mu a t is not greater than, this doesn't hold, minima of mu a x in membership grades of x and membership grades of y. So that is why this set is a non-convex set. So where is the gap? So this is what I wanted to tell you. This is the region. There's a dip in this region. So that is why you can directly say that this is a non-convex fuzzy set. Let us move and understand this through an example. Here I am ready with an example. So this is an example. It represents the membership grade. So I'm drawing this. So we have this x, y. Let us plot these points. What points? 1, 2, 3, 4, 5. So 1, 2, 3, 4, and 5. Okay, and then we have, it takes value 0 for x less than equal to 1. That's okay. X minus 1 between 1 and 2. So let us make a dotted point. It takes value this, x minus 1. It is governed by x minus 1. And then it is governed by 3 minus x. Okay, and then it is governed by x minus 3, right? X minus 3, and then it is governed by 5 minus x. And yes, here this one represents the membership value mu a, and maximum value is, here is 1. So you can see the representation of this fuzzy set. The membership grade is also given. Now I have one question here. So you have to tell me, is this set a normal fuzzy set? Second, is this set a convex? So regarding convex, there's a dip in the figure. You can see here this dip in the figure. So that is why you can directly say that this is a non-convex fuzzy set. But I need a point. You have to tell me a point in the comment that let us take, say, x is equal to, you can take x is equal to, let us take 2.5, maybe you can take here x is equal to 2.5, then what should I take, y? Or you can choose any other xy set and give me the value of t, which is lambda x plus 1 minus lambda y, so that it comes out to be non-convex